Welcome to qnawire.
All right, we need to show the Dieckmann condensation of the following 1,6-diester dimethyl adipate. So let's just draw this out and recall that this is taking place in basic solution, basic conditions, I should say. And yeah, so we're going to have some sort of base, and that's going to deprotonate an alpha proton, right? And create our enolate. It's typically the first step of any sort of keto ester, any sort of condensation or Claisen condensation in basic solution. And what have you done after creating the enolate ion is you've created nucleophilic carbon, right? So we can have this double bond, negative charge in the oxygen pushed back down to reform the double bond, the carbonyl. And then this double bond through the alpha carbon will attack our other carbonyl, right? So pretty standard for any sort of condensation reaction so far. Now here's the part where we've created a cyclic molecule, and I find it helpful to number our carbons, or number the carbons that will be participating in the becoming the cyclic molecule, right? So I like to start at the alpha carbon and call that carbon 1, 2, 3, 4, 5, right? So we know we're going to get a 5-membered ring. So I just start by drawing any old 5-membered ring. Okay. And then, I can arbitrarily number these 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5. Okay. And from here, I can just sort of attach what I see attached in my previous step, right? So, for example, carbon 1 has a carbon attached that should have a carbonyl. And it is, in fact, an ester still, right? The other attachment is taking place at carbon 5, where we should have a negatively charged single bond to oxygen, as well as a methoxide, right? So this is where we're at. Okay. Now, finally, this is basically an E1CB, where we form this double bond and push off the neighboring methoxide, or reform the double bond and push off the neighboring methoxide. Recall that this is kind of uncommon to push off methoxide as a leaving group. We're used to seeing it, in its protonated form, but we're in basic conditions. This definitely happens. Okay, so now we redraw our 5-membered ring. We can know what's at carbon 1. And now we should have a double bond to oxygen on carbon 5. Okay. Now at this point, we've got methoxide floating around, right? We generated methoxide. We're going to utilize that methoxide, in fact, to deprotonate. I'm going to call it OME, right? That's our methoxide ion. And we're going to deprotonate this proton here at the alpha carbon, right? This is alpha to both carbonyls. And that's going to push this carbonyl, the carbonyl without the methoxide now, back up onto here. Okay. Sorry, got a little cramped there. Right. And that's basically it It's just that, if we want to get the final product in the keto form and not the enol form, we want to do like an aqueous acidic workup, right? So H plus H2O would push this, I guess, into essentially, this would push down, just basically undoing the last step. And that may seem kind of pointless. I guess it kind of is, but in a sense, the idea is that if you stopped right here in basic solution, in fact, you'd end up with this product, the enolate. So if you want the diketone, then you're going to want to do an aqueous workup.